Initial startup testing of a restored 1915 750 HP wound-rotor motor at the Gayoso pumping station confirms reliable operation after rewinding, safeguarding Memphis by pumping massive stormwater volumes into the Mississippi River. The Sulzer stationary engine from 1929 is a remarkable example of early 20th century heavy industrial diesel engineering, and every public demonstration of this mechanical giant is a rare and memorable event. Engines of this scale and age have largely disappeared from active service, making the opportunity to see one running under its own power increasingly uncommon. This particular Sulzer engine is preserved not merely as a static exhibit, but as a fully operational machine, allowing audiences to experience the sound, motion, and presence of a true industrial titan from the interwar period. Sulzer, the Swiss engineering company behind this engine, was globally respected for its advanced diesel technology, especially in stationary power generation, marine propulsion, and heavy industry. By 1929, Sulzer engines were already known for their robustness, fuel efficiency, and exceptional longevity. This stationary unit reflects that reputation clearly. With a total weight of approximately 21.5 tons, including its transport frame, the engine embodies the design philosophy of the era: massive cast-iron construction, oversized bearings, and conservative operating speeds to ensure reliability over decades of continuous operation. Technically, the engine delivers an impressive 540 horsepower at a relatively modest 500 revolutions per minute. This low rotational speed is characteristic of large stationary diesels, allowing them to produce enormous torque while minimizing mechanical stress and wear. Such engines were commonly used to drive generators, pumps, compressors, or entire factory lines, often running for thousands of hours per year with minimal downtime. Despite its size and output, the Sulzer engine demonstrates noteworthy efficiency. At idle or without load, fuel consumption is approximately 30 liters of diesel per hour, a respectable figure considering the engine's displacement and power potential. This efficiency was one of the key reasons Sulzer engines were favored by industrial operators who demanded both durability and economical operation. During demonstrations, the engine's smooth but authoritative running behavior is especially striking. Each combustion cycle can be felt through the ground, yet the engine remains mechanically composed thanks to its heavy flywheels and rigid frame. The deep exhaust pulses and steady rhythm provide a powerful sensory reminder of how industrial power was generated before the age of compact, high-speed engines. This Sulzer stationary engine is more than a machine. It is a moving piece of industrial history. Carefully presented and documented, including through enthusiast-made video productions, it allows modern audiences to appreciate the engineering skill, material quality, and design foresight that define the golden age of large diesel engines. Brutus is not simply a car, it is a rolling monument to excess, mechanical audacity, and a time when engineering limits were challenged with raw displacement rather than refinement. At its heart lies an aircraft engine of truly staggering proportions, 47,000 cubic centimeters of swept volume, making Brutus one of the most extreme engine-powered vehicles ever driven on public display. The engine, originally designed for early aviation use, dominates the vehicle in every sense. Its massive cylinders, exposed valve gear, and towering crankcase sit openly on the chassis, leaving nothing hidden or civilized. There is no attempt to disguise the machine's purpose. Brutus exists to showcase brute force, vibration, heat, and noise in their most unfiltered form. Every firing stroke sends shockwaves through the frame, the ground, and anyone standing nearby. Starting the engine is an event in itself. The slow, deliberate rotation builds anticipation before the engine finally catches, erupting into a thunderous, uneven idle that feels more alive than mechanical. Throttle inputs are cautious, not because the engine lacks power, but because controlling it requires respect. This is not horsepower delivered smoothly. It is torque released in violent pulses. Brutus is less about speed and more about experience. Yet despite its intimidating nature, Brutus is fully functional, a testament to the skill and courage of those who built and operate it. Brutus stands as a reminder of an era when engineers asked not how efficient, but how big can we go, and then pushed far beyond the answer. Radial is not merely a tractor pulling machine. It is a rolling monument to mechanical excess and engineering audacity. Competing in the 2.5-ton modified tractor pulling class, this Luxembourg-built beast made its mark during the 2013 European season with a power plant that borders on the unbelievable. A Curtiss-Wright R3350, an 18-cylinder radial aircraft engine originally designed to propel World War II-era bombers across oceans. Displacing massive volumes of air and fuel, the R3350 delivers an estimated 4,000 horsepower and a staggering 10,000 Nm of torque. In tractor pulling trim, that power is unleashed in short, violent bursts, where traction, throttle control, and mechanical survival matter as much as raw output. The radial layout, with its exposed cylinders and unmistakable sound, gives Radial a presence that few competitors can match, both visually and acoustically. Throughout the 2013 season, Radial competed in 6 major runs across Europe, including events at Zell, the European Championships, and the Maid-Putton Euro Cup. Each appearance was a spectacle, as the aircraft engine roared to life on the pulling track, translating aviation heritage into ground-shaking performance. Despite fierce competition in one of the most extreme classes in the sport, the tractor demonstrated consistency and reliability. No small feat for a highly stressed radial engine operating far outside its original design envelope. By the end of the season, Radial secured an impressive 5th place overall in the championship standings and 6th place in the Euro Cup. These results reflect not only horsepower, but meticulous engineering, careful setup, and the experience of a team willing to push boundaries. Radial stands as a perfect fusion of historical aviation engineering and modern tractor pulling ambition, loud, uncompromising, and unforgettable. The Rolls-Royce Meteor V12 tank engine, with a massive 38.8-liter displacement, represents one of the most influential armored vehicle powerplants of the 20th century. In this particular case, the engine is mounted on a wheeled test frame, allowing it to be run and demonstrated outside of a tank hull. This specific Meteor unit was recovered in the United Kingdom after being seized from the Iraq War, where it had originally been part of Iraqi armored forces. Remarkably, the engine had remained in storage and preservation for approximately 28 years before being brought back into public view. The Meteor engine traces its lineage directly to the legendary Rolls-Royce Merlin aircraft engine, sharing the same basic V12 architecture, bore spacing, and overall design philosophy. However, unlike the supercharged Aviation Merlin, the Meteor was adapted for ground combat by removing the supercharger, lowering compression ratios, and reinforcing components for sustained low RPM, high-torque operation. The result was a naturally aspirated, water-cooled V12 capable of producing around 600 horsepower, depending on configuration, with exceptional durability under harsh battlefield conditions. This engine is believed to have originated from Iraqi Type 6 9II tanks, a Chinese-built development of the Soviet T-54/T-55 series, many of which were upgraded or maintained using Western-derived powertrain technology. Iraq's use of Meteor-based engines reflects the long global reach of Rolls-Royce military engineering and the adaptability of the Meteor design well beyond its original British service in vehicles such as the Cromwell, Comet, and Centurion tanks. After being confiscated during the conflict and transported to the UK, the engine was carefully stored, avoiding corrosion and major mechanical degradation. Its long period of preservation highlights the inherent robustness of the Meteor design, with forged steel internals, large bearing surfaces, and conservative operating stresses. Mounted on a wheeled frame, the engine can now be started, warmed up, and run under controlled conditions, allowing observers to experience the unmistakable sound and presence of a large displacement military V12. Today, this recovered Rolls-Royce Meteor stands not only as a functioning mechanical artifact, but also as a tangible link between Second World War engineering, Cold War armored warfare, and modern conflict history. Its survival and operability after decades of inactivity underscore why the Meteor is widely regarded as one of the most successful and enduring tank engines ever built. The Rolls-Royce Griffon Mk58 first startup with contra-rotating propellers is a dramatic and technically fascinating demonstration of one of Britain's most powerful piston aircraft engines. The Griffon Mk58 is a 36.7-liter V12, originally developed for late-war and post-war military aircraft such as the Avro Shackleton, where reliability, sustained power, and torque management were critical. This particular startup is especially striking because the engine is fitted with contra-rotating propellers, a configuration designed to absorb very high power output while eliminating torque reaction on the airframe. The two propellers rotate in opposite directions, improving efficiency, stability, and thrust delivery. Although the propellers used here are approximately 6 feet in diameter, roughly half the size of the original Shackleton propellers, they still generate significant airflow and load on the engine, particularly noticeable in the windy conditions during the run. At startup, the Griffin's mechanical presence is immediately apparent. The engine's large displacement and high compression produce a deep, authoritative exhaust note, while the complex reduction gearbox smoothly drives the contra-rotating propeller system. As oil pressure stabilizes and ignition timing settles, the engine transitions from a raw, uneven idle to a more controlled and confident rhythm, showcasing the precision of Rolls-Royce engineering. Technically, the Mk58 variant was optimized for high continuous power, making it well-suited for long-duration maritime patrol operations. Features such as robust crankshaft design, reinforced bearings, and advanced cooling allowed the Griffin to operate reliably under heavy loads. The contra-rotating propellers further reduced stress on the drivetrain by distributing torque more evenly. Seeing a Griffin Mk58 run today is rare, and witnessing one start with contra-rotating propellers engaged offers a powerful reminder of the peak of piston engine aviation technology. It is a living example of engineering excellence from an era when mechanical solutions ruled the skies. This is a Pratt & Whitney R2 800 double wasp coming to life during controlled fuel testing with Swift's 100 SF aviation gasoline. Conducted on September 27 and 28, 2011 at Anderson Aeromotive in Grangeville, Idaho, the test focused on one of the most demanding piston aircraft engines ever built. The R2800 start is crisp, followed by a short, authoritative run that quickly settles into its familiar radial rhythm. Early results were significant. 100 SF successfully delivered full-rated power, a performance level previously achievable only with legacy 115-145 purple avgas, marking an important step toward viable high-octane unleaded aviation fuel. Starting a Rolls-Royce Viper ASV-8 turbojet by hand crank is about as unorthodox and captivating as jet engine demonstrations get. Designed as a compact, reliable power plant for trainers and light aircraft, the Viper Mk102 was never intended to be brought to life this way. Yet here it is, awakened through mechanical ingenuity rather than conventional ground start equipment. As the hand crank spins the compressor section, the engine slowly comes alive, airflow building just enough to allow fuel introduction and ignition. The moment combustion stabilizes, the character of the Viper is unmistakable, a sharp, rising whine that quickly transitions into the smooth, confident note of a true turbojet. It is a reminder of an era when jet engines were simpler, more accessible, and deeply mechanical in nature. Equally inventive is the custom 45-degree exhaust deflector, carefully engineered to redirect the hot jet plume upward. The result is a dramatic yet controlled demonstration, proof that even a classic Rolls-Royce jet can be safely and spectacularly run in the most unexpected of settings. This extraordinary machine blends Cold War utility with classic aviation power as a Russian Ash-62IR radial aircraft engine is brought to life on the rugged chassis of a Chevrolet K30M1028. Originally designed to propel aircraft like the Antonov An-2, the 9-cylinder, air-cooled AH-62IR is a direct descendant of the legendary Wright Cyclone, known for its durability, torque, and unmistakable sound. The startup sequence is pure theater. Fuel is primed, ignition is engaged, and the massive radial begins to turn slowly, each cylinder coming alive in sequence. After a few hesitant rotations, the engine erupts into a deep, rhythmic roar, sending pulses of vibration through the truck's military-grade frame. Oil smoke drifts into the air as the engine settles into its characteristic radial idle, uneven, mechanical, and intensely alive. Mounted openly on the Chevrolet K30, the engine dominates the vehicle visually and acoustically. This is not a conversion built for speed or efficiency, but for spectacle and mechanical authenticity. Throttle response is immediate and forceful, with torque delivered in heavy, deliberate beats rather than smooth acceleration. The result is a rolling fusion of aviation history and off-road toughness, where every startup feels less like starting a truck and more like launching an aircraft from the ground. This demonstration places a legendary piece of British aviation history firmly on the ground, as a Bristol Hercules radial aircraft engine is run on a purpose-built towing vehicle designed specifically for high-power engine testing. Originally developed during the Second World War, the Bristol Hercules is a 14-cylinder, air-cooled radial piston engine with an imposing displacement of 39 liters and an output reaching approximately 950 horsepower, depending on variant and boost configuration. As the engine is brought to life, the startup sequence immediately commands attention. Fuel and ignition are carefully managed, and once the cylinders begin firing, the Hercules settles into a deep, authoritative radial rhythm. Each power stroke is felt through the chassis of the towing rig, underscoring the immense mass and torque generated by this engine even at moderate RPM. One of the most striking visual details emerges as the run continues. The exhaust system itself becomes a temperature gauge. The exhaust pipe, initially painted green, gradually shifts to brown as heat builds within the metal. This color change is not cosmetic. It is a clear, honest indicator of sustained exhaust gas temperatures and the sheer thermal energy produced by nearly 2,000 horsepower being converted into motion and sound. Mounted on a mobile test platform rather than an aircraft, the Bristol Hercules can be appreciated in a way rarely possible in flight. Cooling airflow, valve train behavior, exhaust pulses, and mechanical vibrations are all plainly visible. What unfolds is more than an engine run. It is a living mechanical performance, reminding viewers why the Bristol Hercules earned its reputation as one of the most powerful and reliable radial engines of its era. The installation of the GA 110 flywheel log saw, equipped with 8 meters of carriages, represents a major milestone after more than 10 years of complete disassembly and inactivity. This stage marks the first startup of the bandsaw blade, a critical moment that validates years of mechanical restoration and adaptation work. Despite the long shutdown period, there was confidence in the machine's condition, thanks to careful inspection and preparation. Ball bearings, a key concern on heavy sawmill equipment, were dismantled and checked individually. They were found to be clean, in good condition, and free of excessive play, allowing them to be reused. Originally, the saw was driven by a 40-horsepower electric motor powering the main band wheel. Since this motor could not be connected in the current setup, a custom right-angle gearbox was designed and installed, an operation that required significant time, precision, and adjustment. The transmission system involved recovering the original drive pulley, lightly reworked to fit the new configuration. Alignment issues quickly highlighted the absence of a flexible coupling, flector, causing minor movement between components and underlining how even small misalignments can generate mechanical stress. A gearbox, sourced from a sugar beet harvester, was repurposed and installed in reverse to correct the direction of rotation. This gearbox was originally designed to handle up to 150 horsepower, while the current setup operates at approximately 70 horsepower, which proved sufficient after proper adaptation. A complete support frame and a band tensioning system were then fabricated to ensure operational stability and safety. The first test run was highly successful. No abnormal noise, no vibration, and no mechanical shock, despite the considerable rotating mass, far removed from the behavior of a simple power tool. Future steps include building heavy concrete foundations, permanently installing the carriage system, and finalizing the drive unit responsible for carriage movement. Once the band blade is professionally sharpened, the saw will be ready to perform its first cuts, bringing this long restoration project to full operational life. The Duvant 6NN engine represents an impressive chapter in early large-scale diesel engineering, and its first start after restoration is a powerful reminder of the robustness built into these historic machines. Designed as a massive 6-cylinder stationary diesel engine, the Duvant 6NN was typically used for electricity generation or heavy industrial duty, where long operating hours and absolute reliability were essential. Before the initial startup, extensive preparation is required. Lubrication circuits are carefully filled, bearings are manually pre-oiled, and fuel systems are bled to ensure clean, consistent injection. Given the engine's enormous mass and slow-speed design, correct positioning of the crankshaft is critical prior to rotation. Once these steps are complete, the starting sequence begins, often using compressed air or an auxiliary system to overcome inertia and bring the engine up to firing speed. As the Duvant 6NN fires for the first time, each cylinder ignites with a deep, measured combustion, producing a steady rhythm that defines classic diesel operation. The engine settles into a slow, authoritative cadence, with heavy flywheels smoothing rotational forces and minimizing vibration. Exhaust pulses are strong but controlled, reflecting efficient combustion and precise mechanical timing. Technically, the engine is characterized by its large bore cylinders, long stroke, low operating speed, and extremely high torque output. These features allow it to deliver continuous power with minimal stress on internal components. Built with thick castings and oversized bearings, the Duvant 6NN was engineered to operate reliably for decades with proper maintenance. The premier démarrage of a Duvant 6NN is more than a mechanical event. It is a revival of industrial heritage. Watching this giant diesel return to life highlights the craftsmanship, engineering discipline, and durability that defined early heavy engine design. The startup of the Duvant 4VN engine represents a significant moment in the preservation of early large-scale diesel and stationary power technology. Built in the early decades of the 20th century, the Duvant 4VN is a slow-speed, four-cylinder diesel engine designed for continuous industrial duty, typically driving generators, pumps, or heavy workshop machinery. Engines of this class were valued for their immense torque, mechanical simplicity, and ability to operate reliably for long periods under constant load. Before the initial start, extensive preparation is essential. Lubrication is the first priority. Oil reservoirs are filled, and oil is manually circulated through the main bearings, crankshaft journals, camshaft, and valve gear to ensure that all friction surfaces are fully protected. Given the massive rotating components and plain bearings used in engines of this era, dry starts are strictly avoided. Cooling circuits are also checked and filled, as these engines rely on stable thermal control to maintain proper clearances. Involves compressed air introduced directly into the cylinders to rotate the crankshaft and bring the engine up to firing speed. This system allows precise positioning of the pistons and ensures smooth, controlled rotation during the first revolutions. Once adequate speed and oil pressure are confirmed, fuel is gradually introduced. The mechanical fuel injection system, entirely cam-driven, delivers fuel at low engine speed with remarkable precision for its time. As combustion begins, the engine transitions from air-assisted rotation to self-sustaining operation. Each firing pulse is slow, deep, and deliberate, reflecting the engine's long stroke and heavy flywheel mass. Vibration is present but controlled, absorbed by the engine's substantial cast-iron frame and foundation. The exhaust note is steady and rhythmic, characteristic of large pre-war industrial diesels. Once running, operators carefully monitor oil pressure, cooling water temperature, and exhaust behavior. Adjustments to fuel delivery and governor settings are made gradually to stabilize idle speed. The successful startup of a Duvant 4VN is not merely an engine run. It is a demonstration of early diesel engineering at its peak, showcasing durability, mechanical logic, and the timeless effectiveness of slow-speed, high-torque power generation. The Rolls-Royce Diesel C8 TFL test run showcases a piece of heavy engineering built for endurance, precision, and continuous duty. This straight-eight turbocharged diesel engine displaces 16.2 liters and delivers 265 kilowatts of power, designed specifically for locomotive applications where reliability is non-negotiable. As the engine comes to life, its sound is deep, measured, and deliberate, reflecting long-stroke cylinders, robust internal components, and conservative operating speeds optimized for longevity rather than raw speed. Turbocharging enhances torque delivery across the rev range, allowing the engine to pull heavy loads smoothly and efficiently. Every vibration, exhaust pulse, and mechanical rhythm speaks to Rolls-Royce's disciplined approach to diesel design, where balance, thermal stability, and structural integrity are paramount. This test run is not just a startup. It is a demonstration of industrial power engineered to perform hour after hour on the rails. The scene captures a very real struggle between machinery and unforgiving terrain. A Belarus 820 tractor, known for its simplicity and rugged mechanical design, finds itself hopelessly bogged down in a mixture of deep mud and melting snow. At the rear, a heavily loaded trailer stacked with compressed straw bales has also sunk into the soft ground, adding massive rolling resistance and turning a routine haul into a full-scale recovery situation. The weight of the trailer overwhelms the available grip, and the uneven, rutted road surface offers no firm base for the tires to bite into. Despite the Belarus 820's respectable torque and mechanical durability, the conditions exceed what a mid-sized agricultural tractor can overcome on its own. The recovery begins when a heavy-duty truck is positioned on firmer ground ahead. A steel tow cable is carefully tensioned between the truck and the stranded tractor. With controlled throttle input and steady pulling force, the truck gradually takes the load. The cable tightens, the mud releases its grip, and both the tractor and the trailer begin to move as a single unit. In the end, the incident serves as a clear reminder of the risks involved in transporting heavy loads under harsh weather conditions. Mud, snow, and saturated ground can quickly turn normal farm roads into traps, where weight becomes a liability rather than an advantage. The startup of the Société Française de Vierzon Type 402 tractor is a striking demonstration of mid-20th century French agricultural engineering, where mass, mechanics, and ritual all play a role. Built in 1954, this tractor is powered by a massive single-cylinder, horizontal, two-stroke semi-diesel engine with an extraordinary displacement of 10,340 cubic centimeters. Operating at just 630 revolutions per minute, the engine delivers between 40 and 45 horsepower at the belt pulley and up to 40 horsepower at the drawbar, relying on sheer torque rather than speed. Starting the Type 402 is a slow, deliberate process that reflects the technology of its era. The procedure begins with heating the hot bulb, a process that takes approximately 20 minutes and is essential for initiating combustion in a semi-diesel engine. Once sufficient heat is achieved, the fuel cock is opened, the hand throttle is set, and the manual fuel pump is primed to ensure proper delivery. Lubrication is handled manually as well, using a hand-cranked oiler to supply oil to the large bearings and the heavy flywheels. These flywheels, central to the tractor's operation, store enormous rotational energy and must be carefully managed during startup. The engine is brought to life using a manual rocking method, where the flywheels are balanced and then pushed past compression to trigger ignition. One of the most distinctive features of the Type 402 is its ability to reverse the direction of rotation, a mechanical solution used to provide forward and reverse movement through the gearbox. With 5 forward gears, 1 reverse, and a total weight of 3 metric tons, the tractor embodies an era when durability, simplicity, and mechanical ingenuity defined farm machinery. The startup is not just in action, but a performance rooted in industrial heritage. The startup of the Curtiss-Wright R1300 radial engine aboard a 1951 North American T-28A is a powerful reminder of America's post-war aviation heritage. At Okeechobee Airport in Florida, an 800-horsepower 9-cylinder radial designed to train a new generation of military pilots in the early Cold War era. As the engine is brought to life, the massive Hamilton Standard 23D40 propeller begins to turn, each blade slicing the warm Florida air with deliberate authority. This particular run follows the installation of Tempest spark plugs, making the startup not only a visual spectacle, but also a functional test of ignition performance and combustion stability. The radial settles quickly into a deep, rhythmic cadence, characteristic of large displacement, air-cooled aircraft engines. During the run-up, throttle and magneto checks confirm smooth operation across the power range, while oil pressure and temperature are closely monitored. After the test, the oil was changed, completing a routine but essential maintenance cycle. The first start of this Deutz Ma 711 stationary engine marks the awakening of a machine that has been silent for more than 4 decades. Built in 1940, this compact single-cylinder engine displaces 553 cc and produces 6 horsepower at 500 revolutions per minute, modest figures by modern standards, yet entirely appropriate for its original agricultural and workshop duties. Equipped with a centrifugal clutch and hand throttle, the Ma 711 reflects Deutz's practical engineering philosophy, simple, durable, and easy to operate in the field. For much of its life, this engine was forgotten. It spent at least 35 years hidden in a barn, buried behind an old threshing machine and covered in straw, before another 5 years resting under a tarp in a small hall. Time stood still, but the machine endured. When it is finally brought back to life, the sound is restrained yet confident, a steady mechanical cadence that speaks to tight tolerances and robust internal construction. This first start is more than a technical moment. It is a respectful revival of industrial history, honoring the craftsmanship that allowed this small Deutz engine to sleep for generations and run again. The Detroit Diesel 12V149 is a legendary high-output two-stroke engine, renowned for its raw power and unmistakable sound. This V12 configuration features 149 cubic inches per cylinder, delivering a total displacement of 1,788 cubic inches. Rated at 1,650 horsepower, the engine relies on a highly aggressive air system, combining 2 Roots blowers and 4 turbochargers to force air through the two-stroke cycle and sustain combustion under extreme load. Weighing approximately 10,000 pounds, the 12V149 was engineered for severe-duty industrial applications. In this case, it previously powered a 160-ton coal haul truck, where durability and constant high torque were critical. When started and running, the engine produces intense vibration, rapid throttle response, and a deep mechanical cadence that reflects Detroit Diesel's heavy industry heritage. The Rolls-Royce Eagle Diesel is a rare and technically significant engine that reflects Rolls-Royce's experimentation with compression ignition power in the interwar period. Derived from the famous Eagle Aero engine family, it features a V12 layout, robust crankshaft, and heavy-duty internals adapted for diesel combustion. Designed for reliability and long service life rather than high RPM, the Eagle diesel delivered strong, low-speed torque and efficient fuel consumption. Its construction quality, precision machining, and conservative operating stresses clearly demonstrate Rolls-Royce's engineering philosophy applied to early large diesel development. The Deutz V8, featured in this test run, reflects the brand's long-standing philosophy of rugged, air-cooled diesel design. Built around a 90-degree V configuration, this engine eliminates liquid cooling entirely, relying instead on a powerful fan system and deep cooling fins to manage thermal loads under sustained operation. This approach reduces complexity, removes the risk of coolant failure, and makes the engine well-suited for military vehicles, construction equipment, and stationary power units. Direct fuel injection, a heavy forged crankshaft, and individual cylinder heads contribute to durability and serviceability. During the test run, steady oil pressure, consistent exhaust tone, and balanced cooling airflow confirm that the engine is mechanically sound and ready for long-term, high-load operation. The premier startup of the Duvant Type 9 Voss engine marks an impressive moment for one of the most powerful historic stationary diesel generators set still in operation. This engine is a Duvant 9 Voss, meaning a supercharged 9-cylinder unit from the renowned Vaux series, designed specifically for heavy industrial power generation. In bare form, the engine measures approximately 5.9 meters in length, 1.3 meters in width, and nearly 3 meters in height, with an exceptional dry weight of 31 tons, reflecting its massive cast iron construction and robust crankshaft assembly. Rated at 600 horsepower at just 428 revolutions per minute, the 9 Voss delivers enormous torque at low speed, ideal for driving large alternators with high stability. The coupled alternator weighs an additional 13 tons and is capable of producing 350 kVA of electrical power at a high output voltage of 500 volts, suitable for industrial grids and heavy loads. The supercharging system improves cylinder filling and combustion efficiency, allowing this large bore engine to achieve high specific output while maintaining durability. Previously documented in a detailed report, this first restart confirms the mechanical integrity and historical significance of one of Duvant's most imposing multi-cylinder generator engines. This second start attempt of the 24-horsepower RAP semi-diesel captures a rare and slightly unsettling phenomenon that many mechanics have only heard about in old workshop stories. This two-stroke engine does fire, but not in the way it was intended. Due to excessive oil in the crankcase, the engine begins to run almost entirely on its own lubricating oil rather than on injected diesel fuel. At the critical moment, the injection pump is manually blocked, cutting off diesel completely. From that point forward, combustion is sustained by oil mist drawn up from the crankcase. With most of the air intake already restricted, engine speed stabilizes at just over 1,000 RPM, still more than double its normal operating range of 425 to 450 revolutions per minute. With unrestricted airflow, the engine could have accelerated uncontrollably, with potentially catastrophic consequences. Starting challenges added to the drama. The electric glow plug had failed due to a short circuit, forcing reliance on external heating. An acetylene burner finally brought the glow plug to a bright red heat, enabling ignition. Although the engine runs, fuel injection behavior remains abnormal, confirming that further correction is needed before this historic machine can be operated safely and as designed. Bringing a 100-year-old rotary aircraft engine back to life is a rare and captivating moment, and this Gnome Omega stands at the very beginning of aviation engine history. Widely regarded as the grandfather of all rotary aircraft engines, the Omega is an exceptionally scarce 7-cylinder design that defined early powered flight. Producing roughly 50 horsepower at 200 revolutions per minute, its output may seem modest by modern standards, but in the early 1910s it represented a major technological breakthrough. As the engine is started, its unique rotary configuration immediately sets it apart. Unlike radial engines where the crankshaft turns, the entire cylinder assembly of the Gnome Omega rotates around a fixed crankshaft, creating a smooth yet visually dramatic motion. Every vibration, exhaust pulse, and rotating cylinder evokes an era when flight was still an audacious experiment. Watching this engine run today is not merely a mechanical demonstration. It is a direct, living connection to the earliest days of human flight. The 1936 Fairbanks Morse Model 32D is a classic example of early American heavy-duty stationary engine design, shown here running in Pottsville, Oregon, as part of a historical demonstration. Built during an era when durability and mechanical simplicity were paramount, the Model 32D was engineered to deliver reliable power for industrial, agricultural, and municipal applications, often operating continuously for long periods under heavy load. The Model 32D generator sets were valued for their exceptional torque output at low RPM, which allowed them to drive heavy electrical loads smoothly without sudden speed fluctuations. This characteristic made them ideal for early AC generation, where frequency stability depended directly on engine speed. The massive flywheels helped regulate rotation, ensuring steady electrical output even as loads changed. Constructed almost entirely from cast iron and steel, these generator units were designed for continuous duty operation. With proper lubrication and cooling, many ran for decades with minimal overhaul. Fuel flexibility was another advantage. Depending on configuration, Model 32D engines could operate on diesel or heavy fuel oils, making them economical in industrial and rural settings. Rather than being viewed through a modern lens of emissions or efficiency, the Fairbanks Morse 32D should be appreciated for what it represents: a milestone in industrial engineering. It stands as a living artifact, demonstrating how power was generated in the early 20th century and preserving the sound, motion, and presence of an age when machines were built to last for generations. The Lister CS 6/1 First Start showcases one of the most iconic slow-speed stationary diesel engines ever built. The Cold Start series was designed for simplicity, durability, and long service life in agricultural and industrial applications. With a single cylinder, large flywheels, and low operating speed, the 6/1 develops steady torque rather than high horsepower. During the first start, careful decompression, manual cranking, and precise fuel delivery bring the engine to life with its characteristic slow, rhythmic exhaust beat, highlighting the engine's legendary reliability and mechanical honesty.